This next example shows us that we could start with a uniform distribution. Train wait times is one of my favorite examples for a uniform distribution. You might wait 0 minutes, you might wait 5 minutes or 20 minutes if the trains come at constant intervals. I guess I'm imagining I'm in some city with a lot of train service. Maybe Eugene trains don't come every 20 minutes, but I don't live over there, so I don't know. Okay, so I'm going to draw a distribution that starts at 0 and goes to 20. So this is my distribution of x, and I'll just draw a horizontal line like that. And then remember, we learned that this is 1 over 20. 1 divided by 20. The height of the rectangle is 0.05, and the only reason that's true is we want length times width to equal 1. We want the total area of this rectangle to be 1. Now, when we learned about the uniform distribution, I gave you formulas for the mean and for the standard deviation. And we need those in order to go forward. So mu is equal to a plus b over 2. 0 plus 20 over 2 is just 10. So we're using a mean of 10. And the standard deviation, b minus a squared divided by 12, all under a square root. So here you can see I'm working out what is the standard deviation going to be for that uniform distribution. If I take 20 squared and then I divide by 12, and students like to ask me why it's 12. It's just a formula that I use, and I don't really know why. Maybe I should, but I don't know why. So I just use that formula, and I think it probably could be derived from the uniform distribution. And it's possible that I saw that at one point in one of my classes, but I don't really remember talking about the uniform distribution in the past. Okay, so we've got our sigma is equal to 5.77 and mu is equal to 10. And now we're going to take samples of size n equals 50. So that means we have to, I don't know where this data would come from. Train wait times. Maybe individuals are reporting how long they waited. Then we grab samples of size 50 from all of their reports, and we calculate x bar. And according to the central limit theorem, x bar will be distributed normally with a mean of 10 and a standard deviation of 5.77 divided by the square root of 50. And I worked out, what is that? 50, and that's 0.82, 0.8164, so 0.82. And it also said to sketch the distribution of x bar. So what will the shape of the x bar distribution be? Is it another rectangle? No, it's a normal distribution. We've exceeded the requirement of a sample size of 30 or bigger. And so I'm just going to draw kind of a narrow normal distribution. And then I'm going to put 10 right in the middle. And then I can draw tick marks to indicate my standard deviations. And that would be 10.82 and so on. I won't bother going too much further, but I will label that that's the distribution of x bar. What is the probability that an individual waits more than 11 minutes? P of x greater than 11. So when I have a question about x, I use the uniform distribution. when I have a question about X bar, and I have a sample size bigger than 30, then I use the normal distribution. So when I'm in the uniform distribution, area is probability, and so length times width, and I'll shade the area that we're discussing. We're talking about the probability of being bigger than 11, so I'll just say that 11 is right there, and I'm trying to find that area. Length times width. The length of the shaded area is 20 minus 11, so that's 9. 9 times 1 over 20, or 9 times 0.05. Anyway, that gives me 0.45. So 45% of wait times are more than 11 minutes. Now, what would be the probability that a sample mean is bigger than 11? So now I have to use my normal CDF. Second distribution, normal CDF. And I'm looking at the probability. Kind of want to shade it on here. So 11 would be like right over there. And I'm just trying to find that likelihood, so I'm expecting it to not be that high. So 11 is my lower bound. Upper bound is 1E99. And you might say, well, the biggest wait time is 20. We could put 20 in there and see if it changes anything. Okay, 10, enter, and 0.82. This should be equivalent to 0.82, right? That's what I said earlier. Enter, paste, enter, and I'm getting 0.11. And if I go and do this again, and this time I just put in 20, I'm just curious if this is going to change my results. Totally the same. So using 1E99 is overkill. Going up to 20 would have been fine as well, but that's what I trained you to do earlier. So 11% of the sample means would be bigger than 11. That's just a coincidence that they were both 11s. Okay, so that's train wait times with a uniform distribution as the underlying distribution. One more set of questions here. According to Boeing data, the 757 carries 200 passengers and has doors with a height of 72 inches. Assume for a certain population of men we have a mean height. When I read this, I immediately want to start writing X is distributed. Assume heights are distributed normally. I was like, can I just assume that? But it was stated, so that's good. X is distributed normally. We have a mean height of 69 inches. That's just under 6 feet tall, right? 6 feet is 72 inches, so this is 5'9". And a standard deviation of 2.8 inches. I actually got that information off of that Tall Life website we looked at earlier. Okay. What doorway height would allow 95% of men to enter into the aircraft without bending? So what I'm trying to locate is here's all the men. And I know that the average guy is 69 inches. And then I'm going to try to find the 95th percentile. So I'm trying to find the X value that is taller than 95% of men. So inverse normal, 0.95, and then mu and sigma. And this is my area to the left. And that tells me that value is 73.6 inches. So that's the 95th percentile of men. There are some men that are taller than that, and they're going to have to bend over, but only 5% of them. If we sample 100 men, what doorway height is higher than 95% of the sample means? So it's the exact same question, except now it's about the sample means. So if we're talking about the sample mean distribution, suddenly the distribution gets a lot skinnier, and we're trying to locate what X bar value is going to be bigger than 95%. And so inverse normal, everything is exactly the same except for sigma becomes sigma over root n. And that's the awesome thing about this chapter, is it's almost exactly the same. Well, not quite exactly the same, but it is a lot of the same stuff that you learned in chapter 6, except you just need to remember to apply the central limit theorem and change sigma into sigma over root n whenever we're talking about the sample means. So if you go and do this, you get 69.46 inches. For engineers designing the 757, which result is more relevant, the height from 21 or the height from 22? Are you concerned about being taller than 95% of the men, or are you concerned about being taller than 95% of the sample means? The men. That's who we're trying to accommodate. We're not trying to accommodate sample means. Those are not actual individuals that could bump their heads.